Hello everyone. This is going to be a quick video about the math behind the two-scale model I plan on building when my moon globe comes. I did that in a live chat yesterday. I'll link to that below. I talked about it. A package arrived today and I was so excited. I thought it was my moon, but it wasn't. It was for Sarah, but I hope whatever it is, she enjoys it. But anyway, first I'm going to go through what I showed you in the live chat yesterday, a printout, but I'm going to zoom in on it for you. So this is basically my two-scale model that I actually plan on building on the ground. All right, so this is just the upper half because the bottom half really wasn't relevant. It was just, this actual document is, I believe, 20 inches by 20 inches. I did it on Publisher. Okay, so here first we're going to go with the chart. This is as if you're looking down at the ecliptic, or solar system from above down at Earth. The blue thing at the bottom is Earth. There's a little white dot there to the right. That's Earth's axial tilt. This is the prediction in the green lines. These are the ones I'm going to have to follow. And like I said before, I am following the moon's orbit. When I model this, I'm going to just do a straight line because here's the curve. The curve is only deviates from the tangent by about 3 inches. So this is this little gray circle here represents the moon. I'm going to model it at these 5 points. So, and my moon is going to be 6 inches in diameter. So as you can see, there's not much deviation. So I can do the experiment as a straight line. It's fine. Here's the other statistics and other things that were on the sheet in more detail so you can read them. The moon on the right, when I get my model, that's how I'm going to have to set it up so I can look, take photos of it and get it right. But anyway, let's get behind the math. I just want to do this as a separate video. I'm not going to go through this in great detail. You can read it. But this is basically the basic statistics I'm using, where I'm getting, numbers I'm using for the following things here. So you can just read that one slide if you want. I'm not going to go into any great detail on that since the most complicated equation is division. Okay, so here, the diameter of my, I say Luna or lunar instead of moon on this. Sorry about that, but my model's only going to be 6 inches, so there's that. So basing everything off my moon needs to be 60 feet away from my Earth. The lunar orbit at that scale, the circumference modeled as a circle, would be 376.8 feet at the scale I'm using. I assumed 28 days for one lunar orbit. I know the two periods are different. I know one's 27.3, I believe, and the other's 29 days, but it's fine for that. And you get about 13.5 feet per day. Divide that by 24, and you get the moon in my model is going to move a little over half a foot every hour. And this 1.133, I'll explain that later because where I got that from. But I divide I multiply my 0.56 by that 1.133, and I get 1.75448, which is about 1 3/4, which means my incremental moves are going to be 1 feet 9 inches for the 5 5 photos I plan on grabbing during the experiment. Okay. Now, the moon's orbit is inclined to the ecliptic, so I had to take that into account doing this model. Granted, the angle's only like 5.1 degrees, but you had to do a little trig to figure it out. But the moon is not going to be at its highest point at this 5.1 degrees when I run this. It was actually a pain in the butt to find out what the actual angle is going to be. But just for the moon at its highest point above the ecliptic, this is the trig behind that. I'm not going to go into that in any detail for you. You can look at that. But during the March 30th to 31st, 2018, the moon will be moving towards apogee, so its furthest point away, and will be only 3.7 degrees above the ecliptic. Sorry, I forgot to superscript that. But anyway, we plug that in, and we get my height. So my moon is going to have to be about 3.9 feet higher than my Earth will have to be at the ecliptic, all right? And how I got this was I had to go on a star chart that showed the ecliptic, and I did it online, and showed the moon with azimuthal grids over it, so I could draw by hand on it and try to figure out the at what point figure out that 3.7 angle. So that's where I derived that from. It was just me doing a manual measurement. So that's the number I'm going to use. My moon is going to be about 3.9 feet above my ecliptic in my model. All right. Stats and math, and then arc lengths. Why do I have these? Well, my Earth, I'm not at the equator, so I'm going to have to measure out exactly. Now, I'm going to be at 47 degrees latitude, about, which would be 9.844 inches. The closest eighth to that is 9 7/8 inches. So I'm going to have to, when I get my Earth model from the equator, I'm going to have to measure up 9 7/8 inches, and that's going to become my 47 degrees latitude, which I'm going to base my observations on. So that's why this is here, and I used an online calculator for that. Okay, now I used moonrise and moonset Marquette, Michigan. It was the closest large town that the online date and time would recognize. I suppose I could have zoomed in and got it exact, but Marquette's close enough. It shouldn't be a big deal. But anyway, basically the moon, I have a rise time and a set time. So what I did here is it'll be above the horizon for about 12.533 hours, or 12 hours 32 minutes. Well, I have 5 observations, but I only needed to divide it by 4 because I'll have an initial observation. It's kind of the reasoning behind why this is the 21st century, even though the year is 2018. It's that kind of similar logic. But anyway, you divide 12.533 divided by 4, and you get 3.13325. You don't get 3. You don't get 3 hours. So you get about 3.133 hours, and that's going to be the time increment between the photos when I actually do this, if I can actually stay awake long enough to get all 5. So we convert our hours to decimals just because it's easier to work with, and then we convert it back to a time. You go down to the second one here, 22.5 plus 3.133 equals 25.638. Well, there aren't 25 hours in a day, so obviously it rolls over. So that's why I got equals 01.638, which would be 1:41 in the morning, essentially. So that's why that particular equation was done that way. But anyway, I was hoping to have an unboxing for you guys, but I'm sorry I don't. But if you have any questions or comments, please leave them below. Don't forget to like and subscribe, and I hope you learned something.